Joseph is in the business of manufacturing phones. He must pay a daily fixed cost of $2,100 to rent the building and equipment, and also pays a cost of $50 per phone produced for materials and labor. Write an equation for C in terms of P, representing total cost in dollars of producing P phones in a given day. So right here, the C we know is cost. Okay, so we're going to make an equation for cost. So C is, I guess, total cost. And there were two things that were included in the costs. And the first is the rent of the building and equipment. So this is our first cost. And the building and equipment we see is a fixed daily cost of $2,100. So building and equipment is always going to be $2,100. And again, that's the cost for the building and equipment. But then in addition to that, there's also a cost for producing phones. Okay, so we got a phones cost. What we know is that it's $50 per phone. So what happens sometimes is students say, well, it's plus 50 right there. But 50 is just for one phone. We actually don't know how many phones are going to be produced. And that's where the P comes in. P is number of phones in a given day. So it's $50 for every one of those. So if you take 50 and multiply it by P, that will tell us how much it costs for producing the phones. So you have the building equipment and then the cost of production, and we get this equation. Of course, some students prefer to write it where the cost is the slope, 50 times the independent variable plus the y-intercept. It's exactly the same equation. It's just written in a different order, and that's okay too. But either one of these works. So today we got an objective. I know the difference between linear and exponential relationships. Specifically, today's objective is for tables and graphs. So we've done a lot of equations with linearity, but now we're going to just determine, can we tell, looking at a table and a graph, is it linear or exponential? Take 30 seconds, copy this down, then we'll get started. In this expression below, 5 is called the base number, and 4 is called the exponent or the power. And so these two vocabulary words, base and exponent, are crucial for us because we're going to be using this vocabulary often in this unit, right? We got a base, and the 5 is the base here, and the exponent is this 4. Now, what the crap is an exponent? Well, as it turns out, we can go back further than that. If you go back, way back in history, eventually people started, they counted, right? Like maybe you got 5 cows and I got 5 cows and someone else has 5 cows. And that's a lot of cows, right? But instead of counting each one individually, we just said, well, you got 5, I got 5, and they got 5. And what did they do? They added them together. So addition really is just a simplified form of counting. And that's fun, right? Like counting cows and adding them together, and then we figure out how many cows are in the village or wherever the crap this is. But eventually math nerds came along and they're like, we like adding so much that we like to do it so often as well. And they started realizing that they were adding the same thing over and over, right? So if you had 5 cows and I got 5 cows and a neighbor has 5 cows, instead of adding them, they were like, well, we can take a shortcut and then we can multiply. It would be 3 groups of 5. You'd say 3 times 5, and that's 15 cows. And then math people were so happy about it, there was much rejoicing and partying throughout the land. Unfortunately, it was a math party, so it wasn't very exciting, but it was still a party. Now, that's changing from the addition to multiplication, but eventually they started multiplying things over and over and over, like 5, right? Like 5 times 5 times 5 times 5. And when you're a math person and you do that often enough, it starts to annoy you, right? Like if I did 5 to the power of 4 here, this would be the base, which is 5, multiplied by itself 4 times. Okay, so this would be the new expression, but you can see it's much easier to write 5 to the power of 4 like this. And so math people realize, well, we can just create a new format, which they called exponents or exponential form, and here we are. And of course, after that, since they didn't have to write all this multiplication down, there was a new party that was created, but it wasn't very exciting because it was math related. But this is exponential form, which is just a simplified form of multiplication, which I have right here. You can also see that the base, which is 5, is the number that is being repeatedly multiplied. The exponent of 4 here, which is a smaller number in the upper right, I guess, corner of the base, tells us how many times the base is being multiplied by itself. So where this exponent is 4, tells us we have 4 of these 5s all being multiplied together. And when you see something like this reads 5 to the power of 4. It reads 5 to the power of 4. Of course, we don't write it out in words like this because that would be more writing than we want to do, at least as math people. So we don't. We now just write it like this, 5 to the power of 4. It reads exactly the same as writing the words. So again, the base tells you what number is being repeatedly multiplied, and then the exponent tells you how many times the base is being repeatedly multiplied. So this one, the base is 6, the exponent is 4. The 6 is being multiplied by itself 4 times. 1, 2, 3, 4 6s, all being multiplied together. This is going from exponential form, which you could then write, if you wanted to, as repeated multiplication. But if you start with repeated multiplication, you can change it into exponential form, as long as the bases being multiplied are all the same. So here, where 7 is the same, being multiplied 5 times by itself, we can just write it as 7 to the power of 5. So there's reasons to go back and forth. You can start with exponential form, change it to expanded form. You can start with expanded multiplication and then change it into exponential form. It depends on what you're trying to do, and I guess how well you can do it sometimes as well. Something we need to keep in mind is when bases are negative. Now this reads negative 2 to the power of 4. This one right here reads as negative 2 to the power of 4, which kind of sounds like it's the same, but I was trying to emphasize the different parts. Let's look at this one right here. Let's see what this one means. Well, that's negative 2 to the power of 4, but it's an order of operations problem, just like the next one is as well. So right here, remember, you got, for order of operations, you got parentheses, then exponents. So right here, I've got an exponent of 2 to the power of 4, which would show 2 times 2 times 2 times 2. And if you multiply those out, not that I think you want to, you get 16. Well, what about that negative? Well, the negative is applied after the exponent. So you could have just put that negative out in front. So the 2 times 2 times 2 times 2, which is 16, it just makes the 16 negative. In other words, in this problem, there's only one negative here, and so the answer has to be a negative as well. Now, how many negatives, hopefully that kind of clarifies what's happening here, because now I've got negative 2 in parentheses to the power of 4. So this means I got to take the parentheses all together, and then I'd have to multiply it by itself 4 times. So there's 1, there's 2, and I should be able to do 3 and 4. All right, so here now, again, it is an order of operations problem, but it's a parentheses to the power of 4. And now I can see I would probably want to find the sign of my answer, but this one tells me I got 1, 2, 3, 4 negatives. 4 negatives is even being multiplied, so I know the answer is a positive, and then I also know that 2 times 2 times 2 times 2 is 16. Okay, so the second one is positive 16, the first one's negative, and it became a positive because of the parentheses, and there was 4 negatives. 4 negatives makes a positive. 1 negative is odd, 1 is odd, so it makes a negative answer. So we're not going to see too much of this today, but it's good to have that reminder because you went over this stuff last year in 8th grade, and so we're going to see a lot of it. We're going to see a lot of this kind of stuff, just not particularly in this unit, in this section rather. So like I said, we got to be able to tell if tables are linear, and we can tell they're linear by finding ratios of change in a y to x ratio. We have seen this before, ratio of change. We've seen it as slope. And that's why we usually make the ratio as y over x. So you see these lines that are going through here. These are actually changes in purple there. That's changes in y's. And then the red here is changes in x's. So again, it has to be, it's the same ratio everywhere, meaning that if from one y value to the next one, I see that it goes up, let's say 2. And then my x, let's say this one goes to the right 3. Well, I would compare that as a ratio of as 2 to 3. And I don't really care about the decimal. I would prefer to see this fraction. Okay, so that's 0.6 repeating if you're interested. But 2 to 3 is the ratio of change. Now, if we see the next one, that the y goes up 2, and then the x goes to the right 3, it ends up being the same ratio of 2 to 3, right? Because it's a change in y to change in x. And that's okay as long as it remains consistent. But comparing these two is not enough. We have to compare all of them to determine if it is linear. So what can happen here is that you can see sometimes they'll say, well, this one goes up 4, but then this one will go to the right 6. Okay, so my change in y is up 4, and then my change in x is to the right 6. But we see that this fraction, 4 over 6, actually simplifies to 2 over 3. So it ends up being the same. So you can't just say, well, it went up 4, which is not 2, and therefore they're not linear, they're not the same. No, it depends on a ratio of change in y to x, and then we can simplify those if we need to. So this could happen as well, where sometimes they're like, hey, this one goes up 6, and then this one would go up 9. But again, as a ratio, it's a 6 to 9 ratio, but that also simplifies to 2 over 3, to a 2 to 3 ratio. And what we see here is that these are all the same. And I'll emphasize that they're the same by saying they're exactly the same. Okay, when they are exactly the same, that's when we know that we're dealing with a situation that is linear. Okay, if those ratios are the same. If they're not the same, from what I remember, they're only going to give us two options, like the objective said. Is it linear or is it exponential? If we see it's not linear for some reason, then we would say it's automatically exponential. With that in mind, let's take a look at this example. All right, now I'm looking for a ratio of change between y's and x's as I go. And I see there should be 1, 2, 3, 4 ratios. And again, I'm just comparing my change in y to my change in x. And I believe you've seen the change is shown like this before in 8th grade. I guess it depends on what class you were in, but that's the way we did it. And I can see from 13 to 25, that means I would have to go up 12, which is my numerator. Now, some students say, well, how the crap did you get 12? All I did is I took the second value. You have to take the second value, in this case 25, and then subtract the original one, which is 13. 25 minus 13 is 12. So that's how I, excuse me, that's how I got 12. I see the x goes from 1 to 2. Hopefully that's easy enough to do in your head. If it's not, just do 2 minus 1 on your calculator, get 1. But that's a 12 to 1 ratio. Okay, and that's pretty good. But now we got to check all the rest of them as well. So I go from 25 to 37, and then I go from 2 to 3. 25 to 37 also goes up 12. And again, I did that by taking 37 and then subtracting 25. It's always the second value minus the first one. And then 2 to 3 goes to the right one. So this, again, is a 12 to 1 ratio. These two are the same, but again, it's not enough to just compare these ones. We got to compare all of them. So from 37 to 49, again, I would just do, in my calculator, 49 minus 37, which is 12. So it goes up 12. And then from 3 to 4 goes to the right one. That's a 12 to 1 ratio, which is the same. And then from 49 to 61, again, goes up 12. That's my numerator. And then from 4 to 5 is to the right one. So these are all 12 to 1 ratios. We didn't have to simplify any of these, which is okay. But again, we see that all of these ratios are exactly the same. And since they are the same, we know that we are dealing with a linear situation, not exponential. Now, sometimes this gets confused with parallel because these slopes are all the same. Yeah, it's the same slope because we're dealing with the same line. These all create a line. In addition to that, and this is kind of a little bit off the subject, but for a graph, if you wanted to, you could just make these ordered pairs and then graph them, like 113, 225, 337, 449, 561. These are all ordered pairs that go on a graph. They're locations on the grid. But for the most part, we're just comparing the tables. So is this one linear or exponential? Well, we're going to do the same thing that we did on that last one. We're going to create some ratios here and compare them. So I always start with my y's. Again, that's from 10 to 15. I see that goes up 5. But I know it goes up 5 because you can just do 15 minus 10. It's always the second value minus the first one. And that tells us it went up 5, so that's my numerator. And then I see the x, it goes from 4 to 6, that's going to go to the right 2. So it's a 5 to 2 ratio, which would be 2.5, if that matters. But that's just for that one change. But then I got to compare the next change. Well, that's from 15 to 20, which goes up 5. And again, if you need to do 20 minus 15, then do it. But then I compare my x's from 6 to 8, that would go to the right 2. So that's a 5 to 2 ratio again, which means these are the same. But again, you can't stop there. You got to compare all of them. So from 20 to 22.5, again, just take 22.5 minus 20, and you can see this one goes up 2.5. Now, 2.5 is different than 5, but it needs to be compared as a ratio, not just as individual values. So here from 8 to 9, this goes up 1, and a 2.51 ratio, 2.5 to 1 ratio is exactly the same as 5 to 2 ratio, meaning if you put in your calculator 5 divided by 2, you'd get 2.5, which is what we get here is 2.5, okay? Now, it's not enough just to stop there. You got to go all the way to the end. From 22.5 to 25, that would be another up 2.5. And we know since this goes up 2.5, that the x has to go to the right 1, which it does. So again, we see all of these ratios are exactly the same. And since they are the same, we expect this to be a linear relationship, not exponential. But again, you need to be comparing all of the changes, not just one of them, because guess what? Math people are kind of devious this way. I didn't write the assignment, but someone else did. But math people are devious this way where they're like, hey, look at this. These are all the same. And then suddenly this one goes up 2.5, and then this changes too. 2.5 to 2 ratio is not the same, and then you'd have to say it's definitely not linear. So you have to be careful on that. Check all of them. So what you're going to see on these exponential tables is that first off, we should check for linearity, right? So for example, you could say, well, this one goes up maybe 2, and maybe this goes up 1, right? So you'd see, well, that'd be a 2 to 1 ratio. But the next one, maybe this one goes up 4, but the x still goes to the right 1. Now again, as a ratio, that would be 4 to 1. Now, just seeing these two, that they're not the same, right? These do not have the same value. We at least know that this makes these not linear. Okay, we at least know they're not linear. So you can cross that out, and since we're just looking at 2 options for the assignment, you could say, well, they're not linear, okay? But what you'll also notice is once you see that they're not linear, then you're gonna have to check for something else. And that's, well, we usually check for something else. At least we will later, but we're gonna do it today. So what you'll see is that maybe, let's see, let's put some values in there, like, I don't know, 1, 2, and then 2, 4, and then 3, 8, and 4, 16, and 5, 32, something like this, okay? But what you'll notice is that this went up by 4, and then this next one goes up by 8, and then this next one goes up by 16. And you see the changes are just doubling, which means that in addition to that, the 2, you could just multiply that by 2 to get 4, and then 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. And this pattern can continue. But since we're now multiplying by factors, not necessarily adding the same value, we're multiplying by the same value. That's what makes this exponential. Okay, now if the numbers, you can see on this one, I'm multiplying by 2. As my x's increase, the y's also increase. If my y's were to get smaller as I increase my x's, then you're multiplying, but you're then multiplying by a fraction. Okay, now how can we tell what we're multiplying by? All you got to do, it's kind of similar to what we did to find the changes with addition. But you take one value and then take the previous value and just divide them. So this would be 32 divided by 16, which is 2, and that's why we know we're multiplying by 2. And this works everywhere. Like if you take 4 and 2, right there you take 4 divided by 2, which is 2. And again, that means the factor that you're multiplying by is 2. So multiply by 2 throughout. Of course, we're not always going to multiply by 2. Sometimes these will be fractions. Sometimes they'll be bigger than 2. Who knows? But we'll see that as we go. Now in this problem, is this relationship linear or exponential? We should start by just determining if it is linear to start with. So I'm going to take my ratios and I'm going to write them as fractions. I'm going to do this on the left though. So I can see from 62 to 124, again, that would just take 124 and subtract 62, and that shows that it increased by 62. I wrote 64, but I meant 62. Okay, so it went up by 62, that's my numerator, and then my x value goes to the right one. So it's a 62 to 1 ratio. All right, good. The next one, though, I see from 124 to 248, so I'd say 248 minus 124. And I see it goes up another 124. So my ratio there is 124, but my x changes by 1. So once again, I see these are not the same. These ratios are not the same. Which means right now I know they're not linear. So you can pretty much cross out linear there, okay? Now, of course, this means it is exponential, and that's okay, but what I would like to do is show how the changes are happening, right? So we can figure out how the changes are happening. Let's take these values down here and work with them again. But I can see now that if I want to know, since it's exponential, I want to know what they're being multiplied by. So I'm going to take this value, 124, and divide it by 62. Just take the second one, divided by the first one, in this case 62, and then you get 2. So which means 62 times 2 is 124, which means that 124 times 2 would also be 248. And then 248 times 2 would also be 496. Okay, so we see that the factor is always 2, just multiply by 2 as we go. If I wanted to continue this table, I would just multiply by 2 and keep going. I don't want to, but if you want to, you can. Again, this part will be important later. I'm just kind of introducing that. For now, we just know that this table is exponential. This one's going to work pretty much exactly the same way. So first, let's check for linearity. Got my fraction line there. Okay, so I'm going from negative 324 to negative 108. Again, just take the second value, negative 108, and you're always subtracting the first value, which in this case is negative 324. Now that is minus a negative. If you're worried about that, don't, because just let the calculator do that work for you. So in my calculator, negative 108 minus negative 324, enter, and it says, hey, that went up 216 right there. Okay, so that's my numerator, 216, when the x value just goes to the right one. So it's a 216 to 1 ratio. And then from negative 108 to negative 36, again, take the second value, negative 36, and subtract the first one. Negative 108, this will tell us not only how far apart they are, but in which direction. So negative 36 minus negative 108, enter in my calculator, and it says it went up 72. If that were negative, then I would know it went down, but I got a 72 numerator, and then the x goes to the right one. So it's a 72 to 1 ratio, which is definitely not the same as 216 to 1 ratio. So these are not the same, which again is just enough to tell us that it's not linear. So since it's not linear, it has to be exponential. And since we know now that it is exponential, let's figure out what we're multiplying by. Okay, so just like on that last one, I'm going to take these values, let's set them aside so we can figure out what was actually being multiplied. And to do this, I just take the second value here, which is 108, negative 108, and always divide it by the first value, which is negative 324. When you divide these two, you will get positive 1/3. Now, you would get the same thing if, let's say, if you did negative 12 and compared it with negative 36, you would get exactly the same 1/3 ratio. So that means that if you were to take that negative 324 and multiply it by 1/3, you'd get negative 108. If you multiply that by 1/3, you'd get negative 36. If you multiply that by 1/3, you'd get negative 12. So you see that repeated multiplication, which is why this is an exponential relationship. Linear or exponential. So the first part here, we know that if it's linear, the changes by addition or subtraction, they're going to be equivalent ratios, but they will change by addition or subtraction. Exponentials, I guess constant addition or subtraction, but exponentials, you'll see multiplication or division within the table. All right, or you'll see that the addition or subtraction is not consistent throughout as a ratio. Now the equations, we've seen this equation before, y equals mx plus b. We have not seen this one, y equals a times b to the power of x. Thank you. And the other equation that we saw was the direct translation of word problems, where we saw it as ax plus by equals c. This is what we call standard form, where a, b, and c are numbers. Now, the fact that we see that isn't really a problem. We know that we should be able to tell if equations are linear through these two formats for equations, which we've seen. But there's other ways, which we'll get to. What I'm concerned about right now for these next two problems is, can you tell by looking at a graph if it is linear or if it is exponential? Now, as strange as it sounds, it's really as simple as just looking at it. We don't want you to do any calculating. We don't want you to use a calculator for any of this stuff. Just look at it, and you have to be able to tell that it is linear or exponential. If it is linear, it is a straight line. As you can see on this graph right here, that's a straight line. Okay? If it doesn't matter that it looks like this, it doesn't have to be exactly this line. It can be straight anywhere. Okay? If we see that we're looking at an exponential equation, then it's going to be curved in some way. So that's a curved line right there, guys. Okay, so and usually they go forever in some direction. Some of these lines are going to be curved, kind of like a smiley face like this one, which that one wasn't very good, but you may see something like that as well. It's probably not in this unit. Okay. So if you see that a line is curved on a graph, then you can know either way here that we're looking at something that's exponential. Now, since we're dealing with only with y equals a times bx, this equation will produce always a line that looks something like this. It may flip, it may rotate, or I guess reflect over one of the axes, but it's always going to be curved in this manner. But again, the emphasis here is, can you tell just by looking at the graph, is it linear or is it exponential? So with that in mind, if I look at this line right here, I see that what I'm looking at is a straight line. And since it is a straight line, I know if it's straight, it has to be linear. Boom, not exponential. Yeah, so again, please don't feel like you're getting tricked here. We're just asking you, do you know if this is linear or exponential? It's exponential because it is curved. If it were straight for some reason, then it would be linear, but it's not. So it has to be exponential. Again, we're not asking you to calculate anything. We're not asking you to notice this y-intercept at 0, 1. We will, just not yet. Just we want you to see that it's exponential. And then once you can notice that, what we'll see in future lessons is, now that we know it's exponential, we will then be able to write the equation in that exponential form, which we saw 2 slides ago. But this is good enough for this one. That's it. On the assignment, all you're going to see are tables and graphs. Can you tell if a table or graph is linear or exponential? And now we have the tools to do that. So go ahead and pull out the assignment, get started. If you got questions, talk to each other, come ask me, I will help you.